So what we're going to look at today is some stuff around the first task of the assignment. Okay, I'm going to look at a problem similar to what you've been given in task 1, and how you can work out how to fit one of the functions you're familiar with to some experimental data and get a close fit function that is as close as possible to that data. All right, and then how you can use from that, once we've got a function for that data, we can then, I'm going to show you how you can use autograph to do trapezoidal methods and vary the number of iterations you look at, or vary the number of data points you use, and how you can use Simpson's rule. So really just going through how you're going to work on that first task for the assignment. All right. So first up, just going to have a look at some of the functions that you're familiar with from what we've done in maths and what their standard form looks like. So what's the standard form of a linear or straight line graph? Y equals y equals now I'm going to give it to you, sorry, my problem, my fault. Ax squared plus bx plus c. Cubic. Well, any polynomial is this form: ax cubed plus bx squared, it can have a square term, plus cx plus d. Yeah. Standard form of a sine. Yeah, but we want some constants in there to express a sine bx plus c for a phase angle, yeah, and possibly a shift on the end, so a shift up and down. Yeah, you're going to look at that in a minute anyway, what these constants do. Okay, cosine would be similar to that, but with a cosine function. Yeah. Exponential. Y is equal to a constant multiple times e to the power of the x, a multiple of the exponential term, plus a constant on the end to shift it up and down the x-axis, y-axis, and then logarithmic y is equal to ln bx plus c. Okay, so they're the common functions that we've covered or at some point during the maths in the first year and in this year. So certainly cover all the ones that we've integrated and differentiated in our calculus. Yeah. Right. What I want to show you, and you'll be familiar with it because I've used it before, but a useful thing with the program, the online graphing software Desmos, is that we can put these constants in, the A, B's and C's, and add a slider so you can see what the effect of changing that constant does to the shape of the graph. Yeah. So, for instance, if I go to Desmos now and I put in y equals mx plus c, it asks me if I want to add a slider for the constants that I've included. Yeah, because y is the dependent variable, x is the independent variable, and m and c are constants. If I add sliders, I can then move them and look what the effect is. And we all know that m is the slope, so if I increase m, the graph gets steeper. We should also be experimenting with negative values, so a negative slope. Yeah, and then you could also experiment with what c means. It moves the graph up and down the x-axis, the y-axis, sorry. Yeah. If we look at y is equal to cosine, so we got a cosine, open the brackets, bx plus c, and a plus d on the end was the function we had. Put a slider in for all of them. Right, a makes the sine wave taller or shorter. That's the magnitude. Yeah. It's the cosine, not sine, I should have said. B makes is the frequency. Yeah. Makes the period shorter or longer. Okay, and C, I didn't add, no, C is already there. C shifts along the x-axis, and that's the phase shift between that and so you can move it along the x-axis. And D will be what it always is, move up and down a y-axis. And it's actually D is always this point here where the graph crosses the y-axis. So what I want you to do is quickly fire up the machine and just spend about 10 minutes experimenting with those functions, standard functions, and what each of the constants do. Because, just hang on a minute, fitting a graph to some data, what we need to do is find out what values of each of those constants need to be to make that function fit that data. And more about that in a little while. Right, what we're going to look at now is on the second page of your handout, there's some data. Okay, following data is for power of an oscillating machine over a period of 30 seconds. If we could integrate this data, then we can find the energy produced in joules. Yeah, because integrating that data would find the area underneath the curve, and therefore the area under a curve of power, you're determining the energy in joules. Okay, so this is similar to what you're being asked to do in assignment, but with a few differences, different data. Okay, so what I'm going to show you now is how you can enter that data in AutoGraph so that it plots those points, and you can see a rough idea what the shape is. Okay, just going to quickly show you how to enter data on a new graph page, and then I've got one that's already complete, so we can move on pretty quickly. Okay, so when you want to enter data, you go to the data menu and you say you want to enter an XY data set, and then you just enter the data for the X coordinate, 1.6 for the Y, 2, 1.1, I'll do one more, 4, 4 and 0.71. when you've finished the whole data and you click OK, it puts those data points on your graph, and the full version is that. Yeah. So they're the data points that we've got for our data, and we want to be able to. The first thing we want to do is try and in your assignment you're gonna do Simpson's rule and a trapezoidal rule mathematically on that data directly for the first 20 seconds, I think it is. You're also going to use this, what we're doing now, to come up with a function that fits that data, so draws a curve as close to those data points as you can. So that's what we're going to go through now, is the process of working out what function, thinking about what function fits that data, and then how we can work out what the values of the constants are that we need to be able to make a curve fit that data. You all with me with what I mean by that? Yeah. So, which function do you think would best fit that data? Well, where would we head with data that looks like that? Cosine? Yeah. Cosine, sine. Any other ideas? Cubic? You could fit a cubic, yeah. You would have seen in your experimentation with cubic that you can get a minimum and maximum within the types of things as you vary those constants. So it might be possible to zoom in on a cubic and get that to fit that data. Yes. So we got three options: sine, cosine, and cubic. Okay. What I'm going to do is look at how we could fit a sine to that data. Yeah. So first of all, what we want to do is I'm going to take a clip of that. And add it to a new slide here. I'll put it after the data. Paste. Just make it fit the page nicely. So we're thinking we want to try and fit a sine wave somehow to that data. A sine actually goes on a graph like so, and it has the form I sine bx plus c plus d. I need to try and find each of those constants. Yeah? And we want to do it thinking about it mathematically. Yeah? So that's what I'm going to be expecting you to do, is not kind of trial and error, but work out as best you can what the constants should be, what you think they should be, maybe then a little bits of adjustment towards the end of that process to get it as close as possible. Yeah. So what's the first constant you think you might go for here to be able to make a start on calculating those constants A, B, C and D? Sorry? The amplitude. How might you go about finding out what the amplitude is, Lewis? What does it mean? Is it from... So what you're saying is A needs to be from there to there. Are you sure? Sorry? Nope. You can get it from peak to peak, but the amplitude is half of that. Yeah, that's what you should have found from experimentation. Remember in your electrical assignment, oh, you know, you're not doing that till next year. On an oscilloscope, usually measure peak to peak. If you want to know the amplitude, that's actually half of that. Yeah. So what we need to do is try and determine what that distance is and half it. Yeah. So A is the peak to peak divided by 2. Roughly, it's approximately equal to, we ought to be saying. So if we take our top data point and our bottom, if we say top data point equals, and what is it? What's the highest value we got? 2.9. Yeah, bottom data point equals, and our lowest value is 0.16, isn't it? 0.16. That's the 8 seconds. Therefore, A is approximately equal to the difference between them two, 2.9 minus 0.16, top minus bottom. That'll give us the peak to peak. Yeah. Divided by 2. Give me an answer. .37. Yeah. So having done that, remember in your assignment you're going to have to try and demonstrate the process you've gone through here. So you may want screenshots showing how each stage of this works and how it gradually gets you closer and closer to that function. So if we go back to autograph now, remembering that I is 1.37. If I now enter an equation, y equals 1.37 sine x. Yeah. And then there's a zoom all function on it. We need to we want the hand. Yeah. We want to zoom out. Yep. So does it look like, as far as we can see, we've got a function that looks like it's got the right amplitude between top and bottom? It's not in the right place, but if we look at it, we've got approximately 2.5, is it something? There's 1, 2, nearly 3 amplitude in the data, and we got about 3 amplitude in our waveform. Yeah. So as far as that go, so far, we've got something. Well, we've got more or less the right amplitude. We can make minor adjustments towards the end. And just take a snip of that. Go back to here. So, what do you think we could look at next in terms of finding out where that data should be? Oh, you're in this case, you're talking about D, aren't you? D is the shift up the y-axis. Yeah. So let's put that on there. But we're currently, so where we currently are is we've got y is equal to 1.37, wasn't it? Sine bx plus c plus d. And what we're saying now is, just get rid of that one, and we're going to focus on finding out what d is. So how can we do that? Remember what the 1.37, yeah, is the distance between here and here. Do it in a different colour. That's the 1.37. That distance, the same thing going up. Yeah. Currently, the centre of that blue waveform is along the x-axis. You want to try setting it to that, yeah? I think there's a better way to look at it. Yeah. We want this peak to be at that level, and we want that peak to be up there. Yeah. So, can you see that we want to shift this the same amount as the amplitude plus that bottom data point? Yeah. Forget about it being shifted along the... What happened there? Forget about it not being in the right place along the x-axis at the moment, left and right. We want to get this peak from there to there. So it must be, because we're currently the centre of the waveform is on there, it must be 1.37 plus the bottom data point. That's going to shift that peak from there to there, isn't it? So we're saying that D must be equal to I plus the minimum data point. That's 1.37 plus whatever the lowest data point was, which is 0.16. Which is 1.53, isn't it? Yeah. Okay. So, going back to the software, if we now go back to our equation and edit that equation and put a plus 1.5, what was it? 3 on the end. Okay. Now we've got that, so this peak, the bottom peak here is about level with that point there, and the top is level with the top peak on the right hand side. So that's two constants we've found, A and D. Yep, all happy with that? Take snip. Go back to here. New slide. Paste. So we've currently got y is equal to 1.37 sine bx plus c plus 1.53. Yep. What are we going to try and find next? What would you try and find next? Two choices. B and C. B's the frequency. Something to do with frequency. We need to stretch that waveform, don't we? That's a bit condensed at the moment. So we need to reduce the frequency. You certainly, I'd say that you certainly wouldn't be wanting to try and find out what the phase shift is before you got the frequency right, or at least close. Yeah, because you can't see it properly. There's a centre line, roughly. Yeah. Looking at the data, there's a few things we know about frequency. All right. Frequency is cycles per second. Okay. But what we know is we know the time. We know time because we got it on the this is hertz. Frequency is also equal to 1 over the time period for one waveform. Time on x-axis. Beg your pardon. Worst mistake I've ever made, I reckon. Nah. Alright, start on this job. Alright, so frequency is not really. Frequency is 1 over the time period. Okay? And the time period is the time taken for one complete cycle. In our data, so forget the blue line at the moment, can we determine the length of time of a complete cycle directly from the data? But what can we determine the length of time of? Half the cycle. Yeah. We've got half a cycle here. From here to about there somewhere. Is t the cycle of a 2. Yeah? It's about 18 seconds. Yeah? So therefore our full cycle is yeah. So half cycle is 18 seconds. Therefore, t is equal to 36 seconds. And as frequency is equal to 1 over t, therefore f is equal to 1 over 36 equals whatever that comes out as. 0.027. Hope that work. So what we're saying here is, from that calculation, we want B to be 0.027. Going back, edit equation. Well, that ain't right. Ah, I know why. Listen, it's a useful mistake to make. All right. In this form, that's omega. Yep. Omega x. So we need the frequency in angular frequency mode. Yep. So we need to convert the frequency in hertz to omega. Omega is equal to 2 pi times the frequency in hertz. 2 pi times 0.027 equals 0.17, and the units of that are radians per second. That's better. Yep. Okay. Happy with that? So it looks though like our frequency now somewhere near what we need it to be. Yep. Take a snip. No, what that 0.17 is saying is how far that 0.17 is in radians per second. Yeah. But so you've gone from one cycle being 36 seconds, yeah, to finding out what the constant B needs to be in radians per second, and that's why I've done those calculations, these calculations. Yeah. So the whole cycle's 36. Yeah, that's the time period. T. Yeah. Find the frequency in hertz by 1 over t, and then multiplying by 2 pi. Multiplying that by 2 pi gives you that frequency in radians per second. Yeah. All right. And then this axis, although we're saying that's time, that's also to the software in radians because I've got the angle set to radians. All right. A little bit confusing, I know, but it certainly tests how well you understand the function. Yeah. Right, so again, I'll take another snip, put it on a new page. So where we currently are with this function is we've got y is equal to 1.37 sine 0.17 x plus c, don't miss the x out, and plus 1.53 on the end there. Yeah. So now what we've got to do is apply a phase shift to move this peak from there to there. We need that in radians. I want you to think about it carefully. How do you think you can work that out mathematically? Well, it is about half the cycle you want to shift it, isn't it? Yeah. Half a cycle, phase shift. A full cycle is 2 pi. You want to shift it half a cycle, so that must be pi, isn't it? Yeah. So you need, if it's not as easy as this, because this is it quite easy, we can see us on a, certainly if it isn't half a cycle, that's pretty close to it, between there and there. Yeah. So because we got, this is on what, 10 seconds, and this peak is on 38 seconds. So about half a cycle there. No, hang on. That's 10, 18 seconds. Yeah, at half a cycle. So a full cycle. So let's write this down. On inspection, phase shift approximately half a cycle. That's equal to pi radians. Therefore, phase shift C is approximately equal to pi. Yeah, may not be that on your if you had. So what we're saying here is you need to determine the fraction of a full cycle that you need to shift it, and then multiply that by 2 pi for a full cycle, or a fraction of a half a cycle. Do you see how we've done that? So then, if I go back in here to the equation and edit it and put a plus, is it plus pi we need? I'm asking you to think about it. We want to move it later. Yeah, so it means let's try. Well, let's see if it does really matter then. Plus pi. Yeah. No, because that's a complete half a cycle. Whichever way you go, you'll get it right. But if it isn't, then you won't. You'll find out when you do the assignment, Callum, won't you? Yeah, because once I've finished this today, I'm going to let you loose up for the rest of the session on that and start on it. All right. So we've now got a function, right, that pretty much fits that data. I mean, I could argue that you might make a slight adjustment of frequency to bring that data point in a little closer. But pretty much it looks like that function fits that data. So now we've got a function. I want to finish this off as quickly as possible. Clip that and go to here. Add that graph. And our function is that y is equal to 1.37 sine 0.17x plus pi plus 1.53. Yeah, and that's kilowatts, because they're what the units of the data were. Yeah. So in the assignment, what you've got now is a function. In the assignment, you're being asked to integrate that mathematically between the limits of 0 and 20. So you're finding an estimate of the area encompassed by that curve, right? And that give you the joules. All the things you've been asked to do in the assignment, you must remember they're all estimates, because this is only a best fit curve. It's not exact. It's the best fit we can find. You're also being asked to use this software, Autograph, to do and to investigate what the effect of applying Simpson's rule and trapezoidal rule to that function. Because you've got a function now, you can select that like any other function graph, and we can right click and we can do find area. Yeah, and then you've got the two rules that we're familiar with. Trapezoidal rule between 0 and 20 is what you're being asked for in the assignment. And how many divisions have we got between 0 and 20? That must be odd. $11. Yeah, but you're being asked in the assignment to integrate between 0 and 20. Because remember, Simpson's rule needs an odd number of data points, doesn't it? So you can add 11 data points in there. Click OK. Shows you how Simpson's rule works, how the trapezoidal rule works. If we zoom in, so you use a box zoom here, this is how you can show how trapezoidal rule works and how adding more data points gives you, because down the bottom here it tells you what the area is, 14.88. Okay, if you do the Simpsons rule again, so sorry, trapezoidal rule again, using start point 0, end point 20, but add more data points. So we done 11 before, so let's do 21. You can see how it's demonstrating how, as you add more data points, these straight lines that cross over the top here are actually getting closer and closer to the curve, and therefore you would expect the result to be more accurate. Yeah. Now there'll become a point where adding more data points doesn't make a difference to the result you get for significant figures, because that's what this software has given me as an answer down here to 4 significant figures. Yeah. So if I add more data points and that result doesn't change, there's little point in me adding more and more data points. So the idea is that you experiment both the trapezoidal rule like so and Simpson's rule with a view to investigating the number of data points that will give you the most accurate answer to how many data points Simpson's rule will take to give you the most accurate answer, as opposed to how many data points using the trapezoidal rule will take to give us the most accurate answer. Yeah. So that's the investigation. So overall, on this task, you're investigating manual Simpson's rule and trapezoidal rule on a piece of paper. Yeah, using the data you've been given. You're coming up with a curve to fit, yeah, so that you can integrate that curve mathematically. You'll be able to compare that integration with the software results that you get doing Simpson's rule using and trapezoidal rule using autograph. So that's that's the task 1 in the assignment. Right, so you now got everything you need to tackle that, and you've got everything that you need after last week to tackle task 2, which is the iterative methods of finding roots. Next week, the first thing I'm going to do is show you how to do the SolidWorks analysis so that you can do task 3, and then the rest of the time till we finish for Christmas is for you to work on getting the data and information you need from these softwares so you can write that report through January. You can do if you want to, yeah. Yeah. You can't. The only thing you can't do on Desmos is that last little bit I now done, the Simpson's rule and the trapezoidal rule. Yeah. So but you can find your function using Desmos if that's what you want to do. Yeah. That's a little bit more. Well, it's not more tricky, but it's different to get the axis right so your graph fill the page. On Desmos, I'll just show you. What you have to do is manually go into the tools up here and set your X and Y axis limits so that you fit your graph to your page. All right, instead of you just use that box zoom on Auto Sketch, was a little bit quicker. Sometimes that's quicker, sometimes it isn't. All right. You can't really box zoom out, can you? That's the problem. You can box zoom in, but you can't box zoom out. So the choice is yours, which softwares you use. Okay. But remember, I'm expecting you to explain mathematically how you find them constants, if that's the type of function you choose. All right. Yeah. This one. Oh, down here. On inspection. Phase, yeah, what we're saying here is, on inspection we can see that the phase shift is never going to be more than half a cycle, because as you've seen, going half a cycle one way or the other way makes no difference. So we could put minus pi in there and we'd still get the same result. Okay, so on inspection we can see that we need to shift half a cycle. If you inspected and you'd only got to shift by 10 seconds, yeah, that would be the shift that you needed to do would be 10 out of 18 times pi. Do you see that? Because we go on a whole half cycle here. It's pi radians. So if we go on 10 over 18, 10 seconds out of 18 seconds shift, we'd multiply that 10 divided by 18 by pi to get our phase shift. Do you understand that?